physics talk. So
thank you so much, Frank. It's all yours. Frank O'Brien, by the way, is our resident NASA Solar System Ambassador. Every month, he gives us a talk about something current or very interesting that is happening in space exploration and associated with NASA. And we're very happy to have him here. Frank has a video prepared, but then he will stay for questions and answers. So Frank, it's all yours. The floor is yours.
Oh, well, thank you so very much. Again, this has just been a wonderful, wonderful setup. Thank you, Lori, for putting in all the effort. It's really paid off. And to the McAfees, thank you, for being here. This was a special treat. Thank you again. One of the things, I normally give a lecture every month at InfoAge in the pre-pandemic era. Of course, that's been kind of nipped at the bud. One of the things which I've discovered I've actually enjoyed learning how to do is creating videos. And I've always, PowerPoint is not your friend. It can be evil, and it's difficult and awkward, and we can beat that up a lot. And so with your forgiveness and indulgence, I really wouldn't mind just simply playing my presentation and put it together. It doesn't look horrible. You don't have to cover your kids' eyes or anything when I'm talking. And I'm not certain if I'm going to be able to monitor the chat to just write down questions and such, but we can certainly meet up afterwards. Videos clocks in at just about 30 minutes, so we'll have plenty of time. Or again, it has been a long day. So now let me see if I can figure out how to do this. Yeah, I can teach you how to go to the moon, but does everyone see this? Does everyone?
now we do.
All righty. Now, I'm gonna start the show. Let me know if you have a problem with the audio. Come on, there we go. Hi, I'm Frank O'Brien, and welcome to the 75th anniversary of the Project Diana moon bounce. I hope all of you have enjoyed the earlier talks we've had. I only wish we were all here to see them in person. Of course, this leads to the most important thing today. I hope all of you and your friends and family are all safe and healthy. I know we're going to be meeting again soon. Our talk today is on space communications, which arguably had its origins with the Diana moon bounce. Although satellites would not become a reality for more than a decade in the future, the work at Camp Evans was an essential first step in making that a reality. Nowadays, we take space communications for granted. Every day, we're greeted and treated with images from weather satellites to rovers on Mars, and hardly give it a passing thought. But like so many of the technologies that are commonplace today, it's difficult to appreciate the efforts in the early developmental stages and what is involved in making it work seamlessly for everyone. Now, first, just a few quick words about me. I've been volunteering at InfoAge for almost 15 years now, and I've been giving talks on spaceflight for much of that time. About 9 years ago, I was selected to become a NASA Solar System Ambassador. This is an outstanding all-volunteer program that takes me into the communities to talk about the NASA mission. No tax dollars are spent on it, and of course, we never accept any kind of compensation. Now, early long-distance radio communications were dependent on the ionosphere and was the basis for the communications network that Marconi created. The ionosphere is an electrically charged region above the Earth, and it ranges from maybe about 30 miles to up to almost 600 miles above the Earth. Now, being electrically charged, it acts like a mirror
to radio waves, allowing a transmitter to bounce its signal from, say, Europe to the United States. But this isn't a perfect mirror. It only reflects those signals in the lower frequency bands, such as under a few megahertz. With such a small bandwidth, radio communications at the time were limited to only one Morse code conversation at a time. But at other frequencies, the ionosphere is transparent to radio signals and can't be used to bounce radio waves off of it. This observation led to the plan for Project Diana to bounce a 111 megahertz signal off the moon. While this is obviously an important achievement, it wasn't a one and done effort. Rather, it was the beginning of a worldwide effort to use the moon for long-distance communications. Researchers at the Jet Propulsion Laboratory in California, AT&T in New Jersey, and Jodrell Bank in England began to regularly exchange voice and telex messages by bouncing their signals off the moon. This was a huge improvement over the existing method of using the ionosphere, which at the times was unreliable and subject to changes that really weren't easily predicted. As is often the case, there's very few technologies that escape being used in that timeless cat and mouse game of spying. Unable to send aircraft over the Soviet Union, intelligence agencies pointed their antennas toward the moon just to listen. Their patience was rewarded, as they were able to receive Soviet radar signals that were bounced off the moon. From these weak signals, the military was able to determine important capabilities of the Soviet air defense system. The Navy was particularly interested in using moon bounces to communicate with ships at sea. By 1960, they were regularly communicating with a ship in the Pacific, allowing a large amount of voice and telex messages to be sent. The quality of the moon bounce signals were so good, it was even possible to exchange facsimile pictures between ships and land installations. Now, while this technology was significant because it could be used to send messages to ships anywhere at sea, there's only one small problem. Any ship at sea that had the moon above the horizon could receive those signals, including our adversaries. And as a result, communications were not especially secure, which, as you can imagine, is a real detriment for military operations. A key benefit was that the technologies were evolving at such a fast rate, and the necessary ground infrastructure was in the process of being built. Everything was in place for the next step in communications. Leading up to 1960, the idea of an active communication satellite, one that would receive a signal from the ground, amplify those signals, and send them back to Earth, was simply not practical. The small size of satellites of the day, which was necessitated by the meager payloads of the existing rockets, which were very small by today's standards, and their limited electrical power, forced NASA to return to the idea of a passive repeater satellite. Originally intended to study the density of the upper atmosphere, a 100-foot balloon was developed and codenamed Project Echo. In one of the earliest collaborations between NASA and private industry, AT&T Bell Labs was brought into the project to see if using an orbiting reflector could be used for long-distance communications. Although the first flight failed to reach orbit, the second Project Echo balloon was successful in 1960 and was followed by its successor in 1964. Project Echo was incredibly successful, but it really was limited in its practicality. Still, it was a very important first step. AT&T Bell Labs built a horn-shaped antenna in Homedale, New Jersey to receive the signals from Project Echo. A horn-shaped antenna was really a preferred architecture as it was highly directional, very sensitive, and had very little noise in its amplified signal. Oh, if this antenna looks familiar, it should be. After being used for Project Echo studies, scientists at Bell Labs used it to research radio signals in the Milky Way galaxy. While this research was important, what they found was enough to win them the Nobel Prize. Their discovery? They confirmed that the origins of the universe was the Big Bang. Now, the days of passive, simply reflecting satellites was nearing its end. In an unprecedented move at the time, A&T contracted with NASA to launch and provide active communication satellite named Telstar 1. Unlike communication satellites today, its orbit only allowed about 20 minutes of service every 2.5 hours. This was not a practical solution, to be sure, but as an engineering test, it was wildly successful. Telstar 1 was the first in an ongoing series of satellites that continues today. Each one has far more capability than those in previous generations. Not only did Telstar provide voice and data circuits, it was to provide the very first live television across the continents. Almost instantly, the phrase live via satellite was pressed into the collective consciousness of mankind. For the very first time, viewers around the world could see wars, coronations, and other world events live on television. It's a complete understatement that this was a transformational technological marvel. Now, our journey from Project Diana through the communication satellite revolution and its impact on everyday life could easily go on for another couple days. We're going to stop here because space communications are more than simply enabling phone conversations or broadcasting reruns of Gilligan's Island. Additionally, there are hundreds, if not thousands, of satellites in orbit right now, all of them eager to return their scientific data. At the same time, yes, there are millions of people on Earth desperately wanting to watch the latest blockbuster movie or follow the latest sporting event. All of these consumers of data originating from space satellites all face the same constraints: frequency allocation, bandwidth, and tracking stations. Now, in talking about radio and space communications, we're going to move away from the voice and television satellites we're all familiar with. An equally important use of satellites is for science and Earth observation. Each of these, from the Hubble Space Telescope to the string of weather satellites you see here, are all collecting volumes of data and need to send it to the users on the ground. This requires a large network of tracking stations all over the world to enable continuous contact. This network is necessary because while the orbit of a spacecraft is very predictable, it rarely shows up at the same place and time on any given day. In fact, the Tyros satellite, which was tracked by the dish at InfoAge, was often out of view for days at a time. By the middle of the 20th century, scientists realized that they needed deeper insight on the aircraft, rockets, and eventually satellites they were building, and how well they were performing. And as importantly, they needed to return all of that scientific data that they were collecting. The solution was to encode all of the important engineering parameters and science data into a radio signal. Now, while this sounds like a difficult task, the basic principles have been around for decades. After all, if it was possible to encode your voice on a radio signal, it should be straightforward to do the same with other data. And fortunately, it was. From this came the idea of telemetry, where the variety of information, from temperatures and voltages on the spacecraft to images of the Earth, were all combined into a single signal and broadcast back to waiting scientists. As spacecraft became more capable and their science requirements grew, so did the need to send ever more vast amounts of data back home. And as just one example here, the SMAP satellite, which is studying moisture content of the soil on Earth, sends back about a terabyte of data every day. That's enough to fill a well-provisioned desktop computer in a single day. Multiply that by the thousands of satellites that are operating today, and you can see that the amount of information being returned could easily overwhelm our ability to collect it. Now, we all have a basic understanding of radio and the frequencies it operates at. An important idea is that each radio station is assigned a unique frequency so that they don't collide with one another. After all, if your favorite radio station used the same frequency as a station you didn't want to listen to, how does the radio decide between the two? Well, it can't. And you can't just use any radio frequency either. To avoid what would be a jumble of competing radio signals, the international community has decided to restrict and assign specific frequencies for distinct purposes and users. At the same time, the higher the frequency goes, the more information it can carry, whether it's computer data, phone, television, or images of faraway planets. Lower frequency signals, like AM radio, are perfectly fine for sending voice, but high quality music needs higher frequency. This is why talk and news shows on the radio are usually limited to AM bands, and the music is broadcast on FM. If you want to send large quantities of data, whether it's on your home Wi-Fi or your phone, you will need to use ever higher frequencies. And even with that, many times it still needs to be shared. As spacecraft evolved to send back even more vast quantities of data, they required higher and higher frequencies to encode all of it. But the number of frequencies aren't unlimited, and there are serious limits to what can be received on Earth. The atmosphere blocks a wide variety of wavelengths, which on the whole is very good. And luckily, there is a wide opening for the radio signals we use today. Still, you'll notice some peaks, absorption peaks, as we call them, near the centimeter wavelengths. This is caused by just the water vapor in the air, and more importantly, rain. Did you ever notice that during a heavy rainstorm, you might have problems with your satellite TV? That's the signal being degraded and absorbed by the water in the air. So, with all of these constraints, how do we service all the hundreds and perhaps thousands of productive satellites in orbit? With the thousands of satellites that are active today, needing to be contacted, there are countless tracking sites set up all over the world. Time on each dish is in high demand, as generally only one satellite can be tracked at a time as it moves across the sky. With such limited resources, data can't be returned to Earth as frequently as desired, which will really limit its usefulness. Now, as you can imagine, building so many ground stations can be really pretty expensive. There are, of course, solutions to this. Did you know you can order satellite tracking on Amazon? Hey, you get your books, your movies, your toilet paper on Amazon, right? Well, okay, you can't buy a tracking station on Amazon, but they have expanded into offering satellite tracking. No kidding. Amazon offers satellite ground stations as part of its portfolio. And they aren't the only one. Microsoft has now entered the field as well. This shows how incredibly strong the demand is for satellite up and downlink services. But they are still quite limited and have only a few ground stations, although they are continuing to build up. But this is certainly not enough to support near continuous contact with critical spacecraft. NASA recognized this problem and came up with a really incredible idea. Why not put the tracking station in orbit? With the demand for the ability to command and receive data from satellites growing faster than new stations could be built, NASA launched the first in its series of tracking and data relay satellites. We call them TDRS. And these were launched starting in the early 80s. Each TDRS satellite is in geostationary orbit and acts as a tracking station with many key advantages. Most importantly, each TDRS can service dozens of satellites at once, relaying commands. Because they are in an orbit far higher than the satellites that use this service, they're in view for 30 minutes or more, rather than the 5 or 6 minutes a ground-based station can achieve. Being in a geostationary orbit, they hover over a fixed spot on Earth, so TDRS only requires a single ground station to support them. The 9 TDRS satellites that are in service today allow for near continuous contact with hundreds of satellites. For spacecraft like weather satellites, the ability to constantly return data ensures that the most up-to-date information is available to forecasters. Also, when rockets, and during its time the space shuttle, were launched, they fly out over the ocean and quickly go out of range from the traditional ground stations. TDRS provides essential radio contact during that critical phase of their missions. In the end, as you can imagine, TDRS has become a critical part of NASA's communications infrastructure. So, TDRS is essential for planets orbiting the Earth. But what about those that are incredibly far away? Spacecraft traveling to Mars are hundreds of millions of miles away. And the two Voyager spacecraft are now about 20 billion miles away, far further than any other spacecraft. This distance makes the received signal impossibly weak by the time it reaches Earth. Such a faint signal is impossible for TDRS to receive, and so the signals must be sent directly to Earth, where gigantic antennas with powerful amplifiers are needed to extract the data being sent. A collection of antennas in California, Spain, and Australia form NASA's Deep Space Network. Together, they form the link from Earth to the furthest distance probes. Almost from the beginning of the space age, each time a spacecraft was sent to a new, further destination, the Deep Space Network was upgraded to handle those weaker signals, the higher data rates, and the more complex encoding of those signals. Another function of the Deep Space Network is for tracking and navigation. Using impossibly precise atomic clocks, the positions of the spacecraft at the far ends of the solar system can be known to centimeter precision. Here in Goldstone, California, is one of those monstrous dishes. The dish itself is 70 meters across, about 230 feet, which is almost 4 times the size of the Tyros dish at InfoAge. It's been recently upgraded with an impossibly sensitive receiver and can now hear the barely detectable whispers of signals from faraway spacecraft. At the same time, arrays of smaller antennas are being built at each site, which will be networked together and introduce advanced technology with those much smaller antennas. The Deep Space Network is operated by NASA's Jet Propulsion Laboratory, which is the center responsible for almost all of the missions to the planets. At this point, we have to ask about the future of space communications. The limits of existing technology, radio spectrum, and the basic laws of physics makes dramatic improvements in radio really pretty unlikely. Serious work is underway right now to transition from radio-based communications entirely and replace them with lasers. Now, if this sounds like a bit of science fiction, well, it shouldn't. In principle, it's almost the same thing as using a fiber optic cable that, we've used these for decades. Of course, minus, the fiber optic cable itself. Fundamentally, all you need is a laser whose signal has been, encoded with some sort of data, and the receiver which takes the encoded light, decodes it, extracts the data, and then sends it along. Doing this on Earth isn't particularly hard, but the problem becomes immense when you're talking thousands or even miles. It's reasonable to assume that you need a powerful laser and a sensitive receiver, and fortunately we have these already. The difficulty is that the laser beam is so very tightly focused, much more so than a radio signal, and because of this, it needs to be aimed with tremendous precision. Fortunately, this is a problem that's been solved for several years. In 2013, a lunar mission called LADEE successfully exchanged data from lunar orbit. That's a distance of almost 250,000 miles. Another experiment this time being run on the International Space Station, was completed in 2014. The results were really quite impressive. Data rates of about 1/2 a gigabit were possible. Now, to put this in perspective, most home broadband is only half of that speed. And as you can imagine, lasers will slowly become more commonplace in space communications. Now, this isn't going to be a solution for all communications, and radio will still have an important role to play. Our journey to explore space and the Earth has an unimaginable amount of knowledge there to learn. Space communications are part of that essential, but often invisible architecture that's part of technology. Through facilities like what we have at InfoAge, people can interact, be entertained, and explore the mysteries of the universe. Thank you for watching. I've hoped you enjoyed this 75th anniversary celebration of the Project Diana Moon Bounce. And as a teaser, I'm going to be talking about the upcoming Mars rover landing as part of our regular lecture series. We're going to be presenting this on January 31st at 2 o'clock. The landing itself is going to be scheduled for February 18th in the afternoon. So until then, please stay safe and healthy.